Good morning. Today's lecture is on radioactivity. Okay, just get me do some introduction. Okay, if you are interested in the video, I want to introduce your friend to the video. You will find that I'm on YouTube to make it more accessible. Right? So the teaching is on physics, A level, Cambridge A level, and you will find that the easiest way to find me is to Google my name. Sorry, not Google my name, YouTube my name. Search for my name. Search for my lecture is harder to find because I'm new in this area. Okay, let us start. If you want more information, right, the notes, the PowerPoint, the video, you can also go to A level, P6, A2. Here, a lot of my notes are here. I will still be developing this Facebook and deposit my notes. Okay, sufficient for the advertisement. Let's start with our video now. Okay, if you have my note, it's on page 352. It's called Radioactive Decay 26.4 according to the syllabus. Right? We want to know the exponential nature of the decay, define activity and decay constant, define half-life, and then show that half-life is related to the decay constant. Right? Decay constant is lambda. These are the reference if you want more information or want to check what I teach. This is the past year paper that I photostat for my student. These are the textbook. Okay. These are the syllabus requirement that has been introduced in 2016. First thing is to remember, look your data sheet. See what is given. This formula is given. This formula is given. Of course, it's better if you can remember the formula. Right? It's faster to solve, but if you've forgotten it or want to check, there's the formula. Right? This one tell you exponential e to the power minus lambda t. Right? This one way of writing. Okay. Right? Types of isotopes. You have natural isotopes, that is, they'll be there. So it'll be there in nature. And it can be stable or it can be naturally unstable. If it's unstable, it emits radiation. Right? We call that radioisotopes. Or it can be artificial, right? Produced by bombarding of stable nuclide with high energy charged particle. It's man-made. Right? We are the one who create it. We are the one who send neutron, protons, or alpha particle into the nucleus. Right? In the previous topic, we studied about binding energy. Right? So we can create artificial radioactivity. Radioisotopes are the isotopes of elements that are radioactive. So instead of calling every time radioactive isotopes, we call it radioisotopes. Background radiation. Natural radioactive isotopes provide most of the background radiation. This one roughly will show you. The green one is the radon, 37%, very high. These are all roughly different, rough value. Different textbook will give slightly different value. But this is just for your information that we are all exposed to radon, thoron gas, gamma rays from rocks and soil. That one we cannot avoid. It's there naturally. And then we have also radioactive elements in our body, carbon-14. Right? We take that one we cannot avoid because it's present in the air. We take food, it's already in the food. Then cosmic ray, that one comes from space. Usually it's highly charged particle. And medical, mainly from X-ray. We X-ray the body, and then fallout, nuclear waste and industry. Fallout with nuclear testing, or it can be the result of our nuclear power station. So we can see 87% of the first four are from natural background. Radon, particular, radon is not that dangerous because it has a very short half-life. It means about, I think, very short half-life. I can't remember. It's less than a minute, maybe. Radon is a different thing. It's about 3 days. So in these 3 days, it's an inert gas. It can move freely everywhere. That is my area of interest in being my master, natural background radiation. And this one can accumulate because as it goes, it involves series decay. Some of it can be bismuth, can be lead, and this decay product is also radioactive, right? And it will be stuck on the dust, and especially in cellar where the dust accumulate, then you can expect the byproduct to accumulate on the dust. Right? In this interesting area, because they scientists to find animals are sensitive because maybe where before the earthquake, the ground will shake and then break before the earthquake, and then this radon gas in the ground will be released. Right? So it's perhaps the animals are sensitive to this one, and they start before the earthquake they run away. Only human being we have lost our sense of maybe sensitive to the environment because of our modern living. Right? So that's for your thought. What is radioactivity? Right? Wherever you go to university, usually school we don't have. Right? Very rare. But in university, yes, you will see the symbol there. Tell you that at that particular region, there is radioactive material. Just to warn people. What is it? That's just a symbol you'll find in university where there is nuclear energy research and radioactivity. What is radioactivity? It's the result of decay or disintegration of unstable nucleus. The nucleus is unstable. So it want to become more stable. It become more stable by the emission of particles. Right? The initial particle or initial element we call it parent is unstable. Then it decay to daughter. These two are different elements, and it emits alpha particle. Sometimes it can also accompany by emission of gamma rays. Right? If the nucleus is still unstable, you want to give out energy, the nucleons may be in an excited state, so that's how it gives out gamma ray to form a more stable nucleus. Right? That's why you have radioactivity. Some may be serious decay. They will keep on giving out particles until they are stable, until this one becomes lower atomic mass. Radioactive decay of the nucleus is independent of environment. So it doesn't matter whether it's an element or the element is joined to another element to form a compound. No, it doesn't depend on it. But it doesn't depend on atmospheric pressure. It doesn't depend on temperature. That's what I mean by environment. The parent and daughter nuclei are usually different elements. These two, plutonium and uranium, different, not the same thing, not the same element. Sometimes you use the word decay, disintegration, or transmutation means the same thing. And it is spontaneous and random. These two terms you need to remember for your exam. Spontaneous and random. Spontaneous decay is one that is unaffected by environmental changes, such as temperature or pressure. Right? So you put in a furnace, it doesn't matter, it still have the same, it still will occur. Now one can control it. You put a high pressure, it can still occur. The only thing that scientists have found that you can control is under extreme condition. You remove a lot of electrons from the atom. Then you can change slightly. Right? That's of no interest to us. That's drastic condition. What is random? The process cannot be predicted. A process cannot predict which particular nucleus will decay next. Right? Usually, you have to look at the mark, and then Cambridge will want you to say is one of constant probability of decay per unit of nucleus, per unit time of a nucleus. Right? We come into that later on in the lecture. So how is the random nature of the emission shown on the curve? Right? It's shown by the emission is shown by the curve, not smooth. Right? Not smooth. Sometimes because it's random in nature, sometimes it may throw out that way, sometimes it may throw out this way, sometimes it may throw more that way, right? It's that way, or no fixed way. Right? Sometimes it may throw out more in one direction, sometimes it may throw out more in another direction. So when we put a detector to measure, we measure in only one direction. Right? That's what I mean by random. CPM here means count per minute. How many particles that we count giving out in 1 minute. How do we know its spontaneous nature of emission? Well, we can measure we can obtain the count, the count rate changes with time. And then we can put it in the furnace, high temperature furnace. And then at the same time, we can measure the count rate with time. And we can show that the curve is almost the same. Same. We look at the half-life is still the same, which we'll study later on. Curve is identical. Or you put high pressure, the same thing, you will see get the same curve. That's what it means by spontaneous. It doesn't depend on the environment. Law of radioactive decay. That one is experimental law. We can measure it, and then what we found, rate of disintegration of a given radioisotope at any time is proportional to the number of atoms and present at time. So if there is greater, then the disintegration is greater. That's what it means at a particular time. So we would prefer to write a mathematical symbol. Then we can understand better rather than all this wording. So that's how we write. This is the number that is emitted per second, or what we call rate of disintegration, equals to minus lambda n. Right? Minus because as time proceeds, is negative. The number decreases. Right? N decreases as the time increases. Right? Lambda is called the decay constant or probability constant. You'll see in a while. That's the Greek alphabet. We call lambda. Right? Decay constant. Let's look at it. Right? Let's rewrite that. Lambda. Right? Won't bother about negative sign there. Right? Dn is just a small change, that's all. So this is more familiar, a small change, the number emitted. Right? Then take this n down. Then down, we have that on there. And then rewrite that. This is probability of decay or fraction decay. Right? Probability of decay. And 1 over n. Right? That one is during that time interval. That small time interval. That is that change. That number that has changed per unit time. So we can say what is decay constant. Decay constant is the probability of decay per unit time. Rate of decay, dn dt. dn or delta n, very small change in the number of particles. Lambda, fraction of the total number of atoms present per unit time. Right? That's what I mean by fraction. The change in number divided by the number present, or probability of decay per unit time, provided the unit of time is small. Don't take too high. That's what it means. Lambda. Unit, right? Delta n and n, same unit, cancel off. So the only thing is you divide by 1 over t, so it's per second. Or we use Becquerel to honor the scientists who did the research, who first discovered radioactivity. Right? Remember that different element or different radioisotopes is radioactive, decay at different rate. And this lambda there is a constant. Lambda is a constant, and we can use this lambda to identify the particular radioactive isotope. And we don't need to go and show that it's a solution, but we need to understand that it's a solution to the differential equation. Remember the original element or radioisotope, we call it parent nucleus. And then the product we call daughter. The other one is the emitted particle. So the number of radioactive isotope at any time, right, that's the solution to the differential equation, where N naught, that's the number present at the beginning. Right? We call it time zero at the beginning. And then this is the number present at time t. Right? Lambda is the probability constant. So what we measure is this one. When we measure radioactivity, we measure the particle that's emitted, number emitted per second, rate of disintegration. Okay? So N is the number present at a particular time. So if you want fraction remaining, number remaining, number present at a particular time, so fraction remaining, we just take the N naught now. Right? So fraction remaining is N over N naught E minus lambda T. Right? I don't think I will spend too much time. Right? This one, if you're interested, you can look up my PowerPoint note and then we can derive the equation. So we won't bother too much about that. K constant and decay constant and half-life of substance are specific to the isotope of the element. It means different radioactive element have different half-life or decay constant. For example, bismuth 210 undergo decay to Tl206 and half-life of 5 days. Whereas bismuth 215 undergo beta decay to polonium 215, half-life of 7.16 minutes. Different. They are isotopes of each other, but they can decay and give different half-life. And we introduce half-life in a while. Activity, right? Or sometimes we call it intensity, is defined as the rate of disintegration of a substance or the number of nuclei that decay per unit time. That's how we define activity. Delta n, the change in the number divided by the time that we measure this number, time interval that we measure this number. And then since that is our law, right? dn dt equals to minus lambda n. Remember, when we measure activity, it's a number. It's a number, a positive number. We don't bother about negative sign there unless we are looking at the law. Right? So it becomes n lambda. We can find activity either by measuring the number of particles emitted per second, or we can just take the number present times the decay constant. Right? Usually it's called count per second or Becquerel or per second or disintegration per second. These are just various units. Same thing, same unit. Right? Activity of the source as detected by a detector and lambda. 1 becquerel is equal to activity of 1 disintegration per second or count per second. Okay, we introduce a unit, and sometimes examiner may ask you to calculate. 1 curie is defined as a quantity of any radioactive material that undergoes 3.0 times 10 to the power 10 disintegration per second. Right? Because sometimes the number of disintegration is so large, we introduce another unit, right? To cater for this large value. So 1 curie is that amount of disintegration per second. And we can show by graph. Right? If the number present, if you look at 100 gram there, at time 0, and if you have a half-life of 5 days, then after 5 days, it goes to 50. After another 5 days, it will be 10 days. 10 days will go to half of 50 is 25. Then after another 5 days, another 5 days will be 15. So half of this 25 is 12.5 and so on. Okay, so usually after 5 half-life, it's very little left. Yeah? So we don't bother to measure it anymore. So let's introduce half-life. It's the time taken for radioisotopes to disintegrate to half their initial number of nuclei, right? From N0 to N0 over 2. That is the time taken that we want. That's called half-life. And it's related to ln 2 over lambda. Ln, this one stands for log to base E. Right? And if we use calculator, we find is 0.693 divided by lambda. So this is given you in the formula sheet. So you can just refer to your formula if you've forgotten about it, but it's always better to remember it. Right? Derivation, sometimes they may ask you to derive. Right? So you derive it from the definition itself. After T half, the number of radioactive nuclei remaining is half the original number, half and not. Then put into the equation. That equation there, put into there. Right? Replace that n as half and not. Lambda still the same, and not still the same because it's a number present initially. And then t, you replace it with t half. And then you cancel the n naught there, right, on both sides there. And then you invert it, right? Or take reciprocal, or take the 2 across there, take this one down there, and then you can rewrite the equation to get rid of the negative sign there, positive. Then you take the ln, right? Taking ln, carry turn to the base E, you got t lambda t half equals to ln 2. You can remember as that formula or rewrite that. That's given the formula sheet. 0.693. Or alternative, we can use reasoning from the definition of half-life. If we start with 0 and not, right? After one half-life, it will be half of it. Half of it will be n naught over 2. Right? After another half-life will be half of this one. Half of this one. Right? So half of this one will be n naught 2 to the power 2. Right? We can continue to work through until we have n half-life. Right? This is 2. That's 2. So if this is n half-life, later, then we have n naught 2 to the power n. Fraction of parent material that remains after radioactive decay can be calculated using the equation. Right? We can have a different equation, n over n naught. Right? There's a fraction remaining. Right? Then we take our n naught to the other side, n over n naught, so it's 1 over 2 to the power n. Right? Where n is the number of half-life elapsed after n half-life. Or time lapse. Right? The time lapse for this value, we can take number of half-life, the half-life. Right? This is another alternative way of calculating. Sometimes it's much easier. Amount remaining, right? After time, the amount remaining is n times half-life or fraction decay. It's just that 1 minus the amount remaining. And then we can rewrite that. Or earlier we got the formula E minus lambda over T. E minus lambda T, sorry. E minus lambda T. And alternative, these two are alternative formula that we can use in exams. Right? We need to know how to draw the graph. Right? If we start with N naught, and if we are given half-life with the isotope, then we start with N naught, mark a point there. Then after one half-life, remember, it decay to half. Then after another half-life, right? Half of this one is 0.25, so it should be here. And after another half-life, 3 half-life, half of 0.25 is half of this one. Half of this one is that one there, over here. Then after another, the fourth half-life, half of this square, right? Half of that one there. Put a point there, and then we can continue on. And then we can, that is the parent, we can draw the curve. That's why you're required to know how to do in exam. How about the daughter? Remember, the parent decreases, the daughter starts to increase. The same thing there. So initially 0, it will be 0. Then this one decrease to half. Your daughter will increase to half. Okay? Increase to half. And then as this one decrease to a quarter, this one will increase to 3/4. There. Or from the top there, like initial value, that 2 square, that 2 square. And then this is 1 square, this is also 1 square. And draw that, and then that is your daughter. Okay, so that is the decay of the parent. There's the build up of the daughter. Daughter start to increase. So as the parent becomes completely 0 at infinity, the daughter becomes completely acquire the value of the parent. The number of daughter increases, and one we have can observe from the draw of sketch. Number of parent decreases with time. At half-life, that is your half-life. Number of parent equals the number of daughter. Right? After that, normal already. After that, the daughter start to increase, the parent start to decrease more. The curve must run parallel to the axis after 5t half. Very close, very close to it, so we say parallel. Showing that the number also does not decrease to 0, but only at infinite time. Right? Very large time, then increase to 0. It will still be some left, but smaller and smaller and smaller time. Okay, natural logarithm or logarithm to base e. Right? Some people will put a time t, there's a number left at time t. I don't need to do that. Right? We are just taking this one, in this value, and take the natural logarithm of it. We got that. Then we can compare with the equation of a straight line. Y equals to mx. Ln n is your y. T is your x. Then we can see that the gradient will give you minus lambda. And then your c, the y-intercept, will give you ln n naught. So we can draw the graph there. That is a negative slope, negative there. So one way to determine your probability constant, lambda, is to draw a graph. Right? Ln it, time, and there is your ln n. Right? Plot a graph of ln n versus t, give a straight line. Your gradient, right? Gradient equals to minus lambda. Your y-intercept here is lambda naught. Right? Use a log linear graph. Plot the activity of material that has 100 becquerel and a half-life of 10 days. Let me just give you an example. Sometimes instead of calculate it out, right, scientists will always look for a way that's easy. Rather than calculate out, we can draw on graph. But graph paper, sometimes we have to do a bit of calculation. But instead of doing that, we use a log linear graph. This is a log linear graph. But log linear graph, we have to, if we start this one with 1, this is 10, this is 100. Or we can start this one with 100 here, or 10 here, sorry, 10 here, and this will be 100, this will be 1,000. Right? Must be every 10. Because all these scale are already taking the log for you. So if we take this one, 10, this will be 20, this will be 30, 40, 50, 60, and so on. Or if you take this one as 1, this will be 2, this will be 3. Okay, no 0. Then that's our activity. We say, initially start with 100. That's a half-life, will be 50. And then after another half-life, it will be 25. And after another half-life, it will be 13. So we can plot the graph. And then we can draw a straight line. And then we can find the gradient. That's what I mean by log linear graph. Right? You're supposed to know, but so far, it only come out in AS. If you can remember. Right? We have encountered this graph in AS. So we press the wrong button. Okay, we've seen this graph before. Let's just review with you where we see that. This one is one of the past year question paper where they ask you is a resistant temperature graph. What is the thermistor resistance correspond to 40 degrees Celsius? So 40 degrees Celsius, they just want to test you. This is a log graph. This is a linear scale. Right? The log has been taken for you. So you just need to read that one there. So this one will be 200. This one 300. This 400. Just getting it to know how to read a log linear graph. Okay, just that. Rather than calculating the log using calculator, we can just do a log linear graph and then get our answer the same thing. Know that it's a straight line. Right? So it's C. Right? We should understand that the half-life can vary from very small, less than 1 second, or it can be millions of years old. That's why this uranium, right, or those that has long half-life, can be used to date initial straw. Right? That's why it's been used to date the age of the Earth. So half-life varies from very small, less than a second, to very large, in billion of years. That's billion of years. Right, let's do some calculation so that we are familiar to know how to calculate. The activity of a piece of radioactive material is 4.3 times 10 to the power 5. Number of undecayed atoms in the material at time t equals 0 is just that. Right? So given information, initially there's a value of n, and that is the activity, sorry. Okay, that's the activity, that's the number present initially. So you want to define the decay constant. So you have to choose the right formula to use. Right? So that's your A. Identify that. That's your N. Then choose the right formula. A equals to N lambda. That's our definition. Then put in your value. There's a value of A. One. There's a value of N. There's a value of N. And lambda is what we want to calculate. Right? Per second. Because this one is count per second. That's why we get per second here. And half-life, use the formula given in the data sheet, formula sheet. Ln 2 over lambda. And then put our value in, use our calculator. This value there, put inside here, and calculate out. Right? Since it's per second, half-life must be in second. The activity of a piece of radioactive material is 4.3. Right? This one we have given now. Yeah. Let's go to part C. The activity after 4 half-life left. Right? After 4 half-life, what's the activity? Same thing. Right? Choose the right formula. You can use that one there or use E minus lambda T. Right? So A naught, initial activity, N is the number of half-life. We are told it's 4 half-life. Then easy to put 4 10 to the power 4 there. This is the initial activity. And we calculate out using calculator, we get this value. Number of undecayed atom after 4 half-life. Right? So basically calculating as the same as initially, A equals to N lambda. Lambda we already calculated. A is this value. Then we calculate put the value in, calculate our N. Right? As I said, not one method of calculating. If you want to use the formula that's given in a formula sheet, go ahead. Right? It's not wrong. Right? You can work it out by step. Long from the definition, initially is 4.3 and 10 to the power 5. Right? At 0 time, after 1 half-life will be half of that. After the second half-life, it's just half of this one there. 10 to the power 5 is still there. Then after the third half-life, half of this one, you get this value. And after fourth half-life, half of this value will be this step. And that's your answer. If you prefer that way, it's nothing wrong. You can show your working accepted by examiner. Right? See part 1 there, I can do that. Okay, don't need to give too many significant figure. You start with 2, so this one by right should be just 2.7. Okay, sometimes we are interested in the activity of the source, but we detect it using a detector. And the detector has a cross-sectional area S, and we place a distance R away. Right? And then AS is the activity of the source. And we just assume that the radiation is given out in all directions equally. Right? That's our assumption, equally. And that's the cross-sectional area S of the detector. We detect the radiation. R is the distance away. And C is the count rate, right? Number of count per second detected by the detector. So we want to calculate this activity, right? But remember, this activity is distributed over the surface area of the circle, 4 pi r squared. And we are just using activity is proportional. Activity, right? This activity that we measure is proportional to the area. That means the bigger this area, the greater will be the count rate activity. Right? Just we are using that. So if that is the activity, that's activity of source, then it is distributed over this area. And if that is the count rate that we measure by this detector, then it's just by this surface area. Then cross multiply, we get an answer. Right? Very rarely this one come up. Very rarely. Right? This side issue, how to measure the activity of the source from the activity we measure by detector. Right? We can also measure half-life that's long. Right? Half-life for 10,000 years, 5,000 years, right? Because within a short period of time, it don't change much. Right? If it's 5 years, then it will only go half. It will only go to half the activity another 5 years. So it's 5,000 years during the short period of time that we measure, even within 1 hour or 10 minutes, it doesn't change much. Measure an isotope with a long half-life. Example, 3 years. Let's measure the activity for 20 minutes and then calculate the number of nuclei per second. Then after that, we can use activity divided by number present. Then we get our decay constant. Then we can calculate our half-life using the formula. Right? This one is for those radioactive isotope that have a long half-life. Short half-life, we used to use graph. Okay, so it is a curve. If it's a lambda is small, then it'll be flatter. And if it's large, it decay faster. That's all. That's what it means by decay constant lambda here. Right? That lambda there. If the decay constant is small, decay slower. If it's larger, it decays faster. Okay, and sometimes we may have encountered there many isotopes there. Usually they won't ask you too many, probably two, but very rarely come up. You can have three isotopes together and you can see that the half-life is a lot of different there. So it means that if we take a log scale here, right, initially this part there, it will be the decay of the smallest one, this one. And then at the end there, after all this decay, after the time of days, where all this one decay and this one decay, this part will just be covered 60, that's all. Right? And since we know that, right, from our log scale earlier, right, our log scale, remember it's a log scale, that's our log scale earlier, it's a straight line, you just find the gradient. Okay, this one has not come out a long time already. Okay, so that's a side thought. This one is for measuring the long half-life. This one is measuring the straight line represent the gradient. Find the long half-life. Right? Find lambda first, decay constant, and then find the half-life. Right? So the first part is mainly decay by the short half-life. And for a longer time, is the decay of long half-life. Application, right? Dating, age of ancient material, determine force painting of about 200 to 300 years ago, dating rocks and prehistoric fossil, carbon-14 dating, right, can be used to date objects to less than 96,000 years, depending on the instrument used. Right? Modern equipment or modern instrument can detect to about 96,000 there. Right? That's why scientists are now discovering that fossils, right, fossils that are millions of years old, right, previously scientists would say there shouldn't be any radiocarbon, but they can date it to about 50,000. So it tells you that fossil is not millions of years old. Fossils are less than that. It's about less than even 50,000 years old if we understand, right? But that's the side issue. There's scientists are debating among themselves. Or the age of the Earth, we can date that, right? Of course, we have to ask ourselves how reliable is that dating method, right? But we are not here to discuss about this controversy. We use the uranium lab isotope dating. We get this date from dating meteorite, right? Because they believe meteorite are the random when the Earth starts. So that's why they date the meteorite. That's from their belief, right? So how reliable is also a matter that scientists are debating. Dating carbon, simple. First, cosmic ray coming from outer space, interact with nitrogen, and then the neutron interact with the cosmic ray interact with nitrogen to form your carbon. Right? Carbon interact with oxygen to form carbon dioxide and mix with the air. Right? In the air, you get C12, C13, C14. So C14 is the radioactive one, and this carbon dioxide is taken by the plant, and then dinosaur animals that take on vegetation will take in the carbon 14. And because if we assume that the earth is very old and that the radiocarbon 14 is constant, then the amount that the animal take in through the lifetime will be the same as the amount that's present in the atmosphere. Right? And when the animal die, sorry, press the wrong button. Okay, so when it die, right? When it die, then it start to decay. So we can roughly estimate from the date the animal died to the present day by measuring the amount of the ratio of C14 to C12, and then compare to the ratio of C14 to C12 that is present today. Right? So this is an interesting area that scientists are saying if the earth is young, then you cannot use this method because the radiocarbon 14 is not constantly increasing. But those who believe in old age believe that the ratio of C14 to C12 is constant. Okay, that's completed there. Radioactive decay, what are things you need to remember? Decay constant, random process. What does it mean? Right? Draw your own mind map to help you remember. And law of radioactive decay. Okay, summarize it. That is the law of radioactive decay. And then from the decay, we can solve the differential equation. We got n equals to n naught E minus lambda t. Then we can show that decay is exponential. Right? Exponential can describe using equation, mathematical equation. Then know what is the meaning of decay constant, probability of decay per unit time, provided the unit of time is small. Right? And then know the definition for activity. Okay? And how to, that's the definition of activity. And then from there we get this value. And then 1 Curie equals that. Sometimes they will give you. Right? Know what is half-life? Right? Time for the radioisotope to disintegrate to half their initial number. Right? Lambda is 0.693 over T half. So know what is fraction remaining. Right? N over N naught. N is the number present at time T. The number remaining is just divided by N naught fraction. 1 over 2 to the power N. Right? And then N is the number of life. Then T is T N T half. As I said, we can use we can use this equation to calculate. We can use this equation to calculate. Either one, whichever is convenient or whichever you prefer. Let's try some partial question. Okay, let's try this one. Half-life of a certain radioisotope is 2 days. The initial count rate of a certain quantity of this isotope was measured as 12,000 counts per minute. The count rate in counts per minute after 8 days. Okay, so you can use formula to calculate. T is time after n half-life is half-life. So you are told that 2 days is the half-life, and then you are told that 8 days. After 8 days, how many half-life? Calculate is 4. Right? 8 divided by 2 is 4. And then you can use this value, activity initial after n half-life is A naught to the power n, and then initially, that's the initial value, to the power 4 to get this value. Or you can use this formula. Nothing wrong with that. Right? Whichever you prefer, you get the same answer. Or as I say, you can use the first method. Right? There's so many methods to do. Okay, let's try to solve this one. A table shows the count rate recorded at a point in laboratory at various times with and without a source in position. From the reading, what is the half-life? When we look at the table, this is with the source, this without the source. So it means that this is the background count rate. We cannot get rid of it. It's always there. Right? So we know this is the background count rate. So we know after 90 days, this is background already. Right? So we cannot use this one to calculate half-life. We have to remove the background activity from all this. Okay, so we need to calculate we need to subtract the background. So we subtract background, 60 minus 20 is 40 for this one, 30 minus 20 is 10, and then the last one is 0. So we see that 40 to 10, right? So if we know the half-life, how to calculate the half-life, we know that from 40 to 20 is one half-life, from 40 to 10 is another half-life. So there are two half-life. So two half-life is from our 30 minus 10. Right? The time is 30, 30 days minus 10 days. Right? From here, we subtract this one, we get 40 to 10. So 40 to 10, right? One half-life, it goes from 40 to 20. Another half-life, it goes to 20 to 10, half of it. So two half-life. Two half-life, to find the time is 30 minus 10. That's what we use. And then we calculate is 10. Normal objective in A level. This is the old question, but it does illustrate things that you need to know how to calculate. Okay, let's do something else. More. Okay, let's try some of the recent past year paper. This one, 2011 June, paper 41. The variation with nucleon number A of the binding energy per nucleon, the binding energy per nucleon, is shown in the figure. On figure 8.1, mark the approximate position of uranium 236, right? Call that Fe. Iron 56, call that Fe. Zirconium 97, and hydrogen 2 on the graph. Right? So the last one is usually uranium 238. That one you should know. Right? They did not see, but you should know roughly. Right? That value is 238 here. And then iron is the maximum point here. Right? Roughly there, iron. Then zirconium, Zr is about 97. So 200 air. This one is about 56. Right? So it's quite near here, roughly. Right? Hydrogen is this part there, somewhere there. Put it there. That's all. Right? Isotope of hydrogen or deuterium. State what is meant by nuclear fission. Sorry. We just get rid of the answer. Okay, state what is meant by nuclear fission. And remember, you forgotten about binding energy, refer to my my lecture under binding energy. State what is being by nuclear fission. Okay, first part. That's all. Nucleus, heavy nucleus, usually it's heavy nucleus, not light nucleus or not nucleus. Heavy nucleus breaks up into two nuclei of approximately equal mass or smaller mass. Approximately, not exactly equal, but approximately equal mass. By reference to 8.1, explain how fission is energetically possible. You explain in terms of binding energy. Increase the binding energy. Right? Binding energy of nucleus is Be times A. Remember, A is the mass number of nucleons in the nucleus. So binding energy of parent nucleus is less than binding energy of the fragment. Okay, that's why it's energetically possible. As long as the binding energy of the fragment is greater than the binding energy of the parent. Okay, sorry. To remove all these answer. Okay. State what is meant by binding energy of a nucleus. Same thing. This is 2011 June paper 42. Right? Energy is energy required to separate nucleons in the nucleus to infinity, right? Or completely. We want to make idea is that we want to separate completely. There's no more force between the nucleons anymore. Show that the energy equivalent of one atomic mass unit is 930 mega electron volt. This one you have no choice. You have to use your data sheet. Right? One atomic mass unit is 1.66 and 10 to the power minus 27 kilogram. You can get from data sheet this value. And then use Einstein relation, E equals to mc square. M is the change in mass. C is the speed of light. One atomic mass unit, change it to kilogram. That's the speed of light. Square that. Use your calculator. You get that. But you want it to mega electron volt. This is in joule. So 1 mega electron volt is 1.6 and 10 to the power minus 13 joule. Right? Or you can convert it to 1 electron volt is 1.6 and 10 to the power minus 19 joule first. You can use that. See, right? The value is the same as the value for electron if you use electron volt. Right? Then you divide that by this one, and you get 930. Right? It's actually 934. But round it off to 930 mega electron volt. Data for the masses of some particles in the nucleus are given in 8.1. Use the data from 8.1 and the information from B to determine the in mega electron volt the binding energy of deuterium. Okay, given the mass of proton, mass of neutron, and then the mass of nucleus in atomic mass unit. So the change in mass is the total mass of nucleon, mass of nucleus. Right? Remember, deuterium has one proton and one neutron. That's why you add these two together. Right? Atomic mass unit, and then this is the mass of nucleus, deuterium. Subtract that, get this value, atomic mass unit. And then since they want it in mega electron volt, you have to use the value that you have derived, right? Times 930. One atomic mass unit is 930. So this value times 930, and then you get mega electron volt, which is very high, very large value. Per nucleon, right? Binding energy per nucleon or zircon, right? Zirconium. Same thing. Right? Total mass of nucleon, right? Yeah. More change in mass. Total mass of nucleon minus mass of nucleus. So zirconium, right? Look at that. That is 40 proton. So 40 times that value, right? That value there is a proton, right? Total mass of proton. And then 97 minus 40 is 57. That's the number of neutron. So number of neutron times this one, this value. Right? So you get, and that's the rest is just, this one is just a mass of nucleus. This one. Let's subtract that and change to mega electron volt per nucleon. Right? You have to change it to mega electron volt and then divide by a number of nucleon. So 0.69 times 930 divided by 97. Right? Total number of nucleon 97 here. Get an answer. Okay, let's try some half-life calculation. Let's remove the answer. Okay, radon 222 is a radioactive element having a half-life of 3.89 days. Radon, when found in the atmosphere air, can present health hazard. Yeah, remember? Can move up from ground to very high in the atmosphere, and as it move up, it will decay to lead and bismuth, and some of these products are poisonous to Earth. That's why it means like health hazard. Safety measures should be taken when activity of radon exceeds 200. Right? Just for our protection. We can be exposed to a certain amount of radioactivity, but more than that, it will damage our cell and provide health hazard to us. Define radioactive decay. Right? Define, you have no choice to memorize it. Right? Probability of decay of nucleus per unit time. Show that the decay constant is this one. So to get the decay constant, we must go to half-life. Right? Convert this one to second first because you want per second. Right? That's the formula that we use. You can go to data sheet or formula sheet to get this formula. Right? So that is take our T half down, got ln 2 over T half. That's your 3.82 days. Right? 1 day is 24 hours. 1 hour is 3,600 seconds. We have to change the days to second. Then we use our calculator. Right? Show the value. Volume of 1 cm cube of atmosphere air is this one, number of molecules. We want the ratio of air, number of air molecules in 1.0 cm cube of atmospheric air, number of radon atoms in 1 atmospheric air. Right? Number of air molecules in 1 cm cube of atmospheric air, number of radon atoms in 1.0 atoms of atmospheric air. Right? One is the radon, one is the air molecule. And we look at what is given. This is given. Atmospheric air contains that amount. For the minimum activity of radon, at which safety measure. So the value of this one is given in the previous calculation. Right? So activity of radon that is given previously, we use this formula. And since we have calculated our lambda, put in our value for lambda. That's our value for lambda. That's our activity. Refer to the previous question. That's our n. And from there, we can calculate our n. Then we want to find this ratio. This one is given. That one. Bottom, the denominator is this value. Put inside there. Right? Value by this value. And use our calculator. Okay. So we have given you some example. So we will end here. Thank you for listening. Hope to see you again.